Time. We experience it constantly, seconds slipping into minutes, days folding into years. We mark its passage with clocks, calendars, and milestones. Yet, when we look beyond our planet, into the great expanse of space, time no longer behaves as we expect. Time, in the vastness of the universe, is far more mysterious, and its flow isn't constant. It is not simply a ticking clock that governs the cosmos, but a dynamic, flexible force. Time itself, it turns out, is an integral part of the fabric of space, and its nature changes depending on where you are and how fast you're moving. On Earth, time feels like a steady, unchanging companion. Seconds tick by, minutes slip into hours, and days transform into years. Time gives us structure. It's how we organize our lives. But this perception of time as a constant, unwavering stream is actually limited to our everyday experiences. When we venture into space, this understanding begins to break down. Time, it turns out, isn't just a linear progression of moments. It is a dimension, much like space itself, and it is deeply interconnected with the very fabric of the universe, what we call space-time. Imagine, if you will, a vast, invisible sheet that stretches across the universe. This is the fabric of space-time, and it behaves in a way that defies our ordinary understanding. Just as a heavy object placed on a stretched rubber sheet causes a dip, a massive object like a planet or a star causes space-time itself to warp, stretching and bending. And where space is bent, so too is time. This warping means that time can move faster or slower depending on the shape and curve of space around it. The true revelation about time came in the early 20th century with Albert Einstein's groundbreaking theories of relativity. Before Einstein, time was assumed to be a universal constant, ticking the same for everyone, everywhere. But Einstein's insights shattered this idea. In 1905, he published his special theory of relativity, which suggested that space and time were not separate entities, but part of a unified whole, space-time. This was the beginning of a revolution in our understanding of the cosmos. Einstein's theory showed us that the fabric of space-time can be altered by mass and energy. When a massive object, like a planet, a star, or even a black hole, exists in space, it warps space-time around it. It's as though the presence of mass causes space to curve and time to slow. Time, once thought to be constant, is now understood to be relative, a concept that fundamentally changes the way we view the passage of time across the universe. This means that time is not experienced the same way by everyone. The closer you are to a massive object, the more space-time is warped and the slower time moves for you. Conversely, the farther you move away from a massive object, the less space-time warps and time moves faster. It's as if time, instead of being a rigid, unchangeable flow, is something malleable, something that can stretch, shrink, and bend depending on the environment. Nowhere is the warping of time more extreme than near the most massive and dense objects in the universe, black holes. These cosmic giants are so powerful that their gravitational pull bends space-time to an almost unimaginable degree. At the center of a black hole lies a singularity, an infinitely dense point where the laws of physics break down. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. Imagine you're an astronaut aboard a spaceship, traveling toward the event horizon of a black hole. As you get closer, the warping of space-time becomes more intense. Time slows down for you. From your perspective, everything seems normal. But to an observer far away, time appears to be stretching. The closer you get to the black hole, the slower your clock ticks compared to someone far away from the black hole's influence. This is a phenomenon called time dilation. To you, the astronaut, only a few minutes may pass as you approach the black hole. But to someone observing you from a safe distance, decades, or even centuries could pass in the blink of an eye. This is not just theoretical, it has been observed experimentally. For example, when we send atomic clocks on fast-moving jets or into orbit around Earth, we measure a difference in the passage of time. The faster you move, or the stronger the gravity you experience, the more time slows for you relative to others. While time might bend and stretch depending on where you are, there's another fascinating feature of time that's always present: its direction. We experience time as something that always moves forward. We remember the past, live in the present, and anticipate the future. This flow of time, this arrow of time, is a key part of how we experience the universe. But why does time only seem to move in one direction? The answer lies in the concept of entropy, the measure of disorder or randomness in a system. Entropy always increases over time. Think about the melting of an ice cube. In the beginning, the ice is in an ordered, low-entropy state. As it melts, the molecules become more disordered, increasing the entropy. This increase in entropy is what gives time its direction. It's as if time itself is tied to the universe's tendency to move from order to disorder. This arrow of time governs everything from the aging of living beings to the cooling of stars and the eventual decay of all matter. In a closed system, entropy will always increase, and the past will always be more ordered than the future. This is why time moves forward for us. It's driven by the inexorable rise of disorder in the universe. Time travel, the ability to move backward or forward through time, is one of humanity's greatest dreams. But could it ever be possible? According to Einstein's theories, time travel may not be as impossible as we once thought. It might even be achievable under the right conditions. One of the ways time travel could work involves traveling near the speed of light. According to special relativity, as you approach the speed of light, time slows down for you relative to someone who is stationary. This means that if you were to travel at near light speeds, you could experience only a few hours of travel, while for people on Earth, years might pass. This type of time dilation is a kind of time travel into the future, but the energy required to reach such speeds is far beyond anything we can achieve with our current technology. Another theoretical possibility for time travel lies in wormholes, hypothetical passages through space-time that could connect distant points in both space and time. In theory, if we could stabilize a wormhole, it could allow us to travel back and forth through time. But like the idea of traveling near the speed of light, wormholes are still the stuff of science fiction, objects that exist only in mathematical equations, with no practical way to create them yet. Even at the scale of the entire universe, time behaves in fascinating and complex ways. The universe itself is expanding, and as it does, space itself is stretching. This expansion of the cosmos has a profound impact on time. As galaxies move farther apart, they appear to be moving more slowly from the perspective of someone on Earth. In the distant future, when galaxies have drifted so far apart that they're no longer visible, time will feel vastly different. The universe, in all its vastness, will become a cold, dark, and distant place, with the passage of time feeling stretched and fragmented. For those who live in such a future, the entire concept of time may be unrecognizable, just as the ancient cosmos was very different from the universe we know today. Time, in the grand scale of space, is not what it seems. It is a living, breathing part of the universe, intricately connected with the very structure of space itself. Time is elastic. It stretches, compresses, and flows differently depending on where you are and how fast you move. The deeper we dive into the mysteries of space, the more we realize that time is not a constant, but a dynamic force shaped by the mass and energy of the universe.